So welcome everyone to the masterclass day of CPAIOR 2021. So the organizers of the masterclass is Nina Nardiska and myself. The title of the masterclass is Explanation and Verification of Machine Learning Models. Let me see. So to give you a bit of rationale, I will just show you this slide, which is taken basically from the internet. You can find lots of images like this on the internet. It's not to upset anyone. We all like machine learning models and the efficiency, which is quite impressive these days. But the idea of the masterclass is to bring the researchers that work on verification and explanations for machine learning models, which of course is used nowadays almost everywhere in all the devices that we have as humans. It affects all aspects of our lives, and I think the range of applications will just grow further. And since it's applied in safety critical applications and in medicine and military, it's kind of important to understand what is happening inside machine learning models, why they fail if they do, and what to do to prevent those failures. And so there are two major approaches to this issue. One is verification of machine learning models, and the other one is explanation of machine learning models. They are tightly related, as was shown recently. That's why we're bringing together the leading researchers in both areas. We'll have 6 talks, and we will have 3 sessions. Each session will obviously have 2 speakers. This is going to be the day schedule. So the first session will start in 1 minute. It will take 2 hours, and then there will be a 30 minutes break, and then there will be the second session and another coffee break and the final session. Each session will consist of a talk on verification of machine learning models and also on explanation of machine learning models. So hopefully everyone will enjoy. Let me stop sharing and let's welcome our first speaker, who's going to be Katz. He's an assistant professor of the Hebrew University of Jerusalem, and he's one of the main authors of such tools as Simplex, which is one of the, I would say maybe the first or one of the first tools that were developed for verification of machine learning models. And it's on applying SMT-like technologies to verify ReLU-based neural networks. And then they proposed also another more advanced tool called Marabou. I'm not sure if that's the right pronunciation. And today, Guy is going to talk about safety in AI systems, SMT-based verification of deep neural networks. So let's welcome our first speaker.
Thank you. Just to make sure, can you hear me okay?
Yes, I do. Yep.
Okay, great. So let me share my screen. Okay, so hi everyone. Thank you for the invitation. I'm very happy to be here, and I'm sorry I couldn't be there in person in Vienna. But you know, that's life. So well, after this very nice introduction, I think all the background has been covered, so I will just jump right into it. So as we have just heard, we have today, wherever we look, we have programming by machine learning. Right? So already machine learning is now dominating many aspects of our lives. And the situation is that you have very complex requirements. You're not sure how to manually write software that will satisfy these requirements. And so you turn to machine learning. You extract examples of how you want your system to behave. You give these examples to a training algorithm, and you get back this black box, for example, a deep neural network, which sort of does what you want it to do, but you're not always sure that it will 100% satisfy your requirements. And so one of the main questions that we are trying to answer, and it seems like you will hear a lot about it today, is how to certify that these black boxes, that these neural networks satisfy the requirements that you start from. So here is, before we dive into how you could do such a thing, here's a little bit of motivation. So I hope this will be visible through Zoom. So what you see here is a video of a Tesla Model S. Right? So that's the Tesla up there on the left. It's in autopilot mode. And you can see it driving happily. And now pay attention to the left shoulder of the road. Okay, so I'm not sure precisely how well you were able to see this, but if you didn't, I will describe it for you. So the Tesla was happily driving on the left lane, and suddenly there was some road construction going on the left shoulder, and this yellow fence appeared, and the Tesla sort of bumped into this fence and was damaged a bit. So in this particular case, this video is also a little bit old now, and it's really not a very severe accident. The Tesla was able to drive on, the damages were pretty minor, but I think the motivation is clear. Right? If you have this, humanity is now putting a lot of effort into autonomous driving. If you want to sit in a vehicle that's being driven around by a neural network, you really want to be sure that this kind of things cannot happen. Another example, which again, I'm sure you will hear a lot about today, is this thing called adversarial inputs. So neural networks have really conquered the world in computer science, and we're using them everywhere. But it turns out that if you take state-of-the-art neural networks and you slightly perturb their inputs, you can get very crazy results. So for example, in 2015, a group of researchers took an image recognition deep neural network. So image recognition is a field in which neural networks really excel. And they gave this neural network an image of a panda. And the network replied, well, sure, this is a panda. And the network also assigned itself a score. So it said, I'm 57% sure that this is a panda. So far, so good. And then the researchers added a little bit of noise. So the square that you see in the middle is a perturbation. And so each pixel gets slightly perturbed. The epsilon means that the perturbation is very small. And when you overlay the perturbations on top of the panda on the left, you get the image on the right, which to the human eye is still clearly a panda. A human cannot see any difference between these two images. Only now the neural network says that this is a gibbon, a completely different animal. And it says so with a very high level of confidence. So 99% confidence that this is a gibbon. So when this thing was discovered, this was very troubling, right? Because up to that point, people thought that maybe neural networks sort of mimicked the way that the human brain worked. But when this was discovered, suddenly we lost confidence a bit in neural networks. And it turns out, so since this was observed, this has been a very active field of research. And it turns out that even state-of-the-art networks today are vulnerable. Right? So we don't really know how to solve this issue. And you might say, okay, big deal, panda, gibbon, who cares? So here's another example, this time from a neural network that is supposed to recognize traffic lights. And it turns out that all you need to do is change 11 pixels, right? So you just add 11 white pixels to your image, and the image turns from a traffic light into a kitchen oven. So again, the ramifications, I think, are clear, right? If you want to sit in an autonomous vehicle that uses a neural network, you want to be sure that these things cannot happen. And this is not a theoretical problem. Attacks have been demonstrated in the real world, and attackers are getting better. Okay, so this is a very pressing issue. And we really want to be sure that we don't have these things in our neural networks before we deploy them. I should have mentioned in the beginning that I plan to stop occasionally for questions. So this is the first break. If anybody wants to ask anything, please go ahead.
So when you say attacks, what's an example of an attack?
So if somebody is out to get you, right, and they know the route that you take to work every day, they can go and they can post some stickers on a stop sign. And this is something that people have really done. They show that you can post some stickers on a stop sign, and suddenly your neural network will no longer recognize it as a stop sign, but instead as an entering highway sign. Right, so if somebody is willing to put the effort into harming somebody specific, then they could possibly engineer this kind of attack. Alternatively, you could say, I'm going to install these neural networks in millions of cars. So statistically, right, some of them are going to make mistakes and some people will get hurt. So either way, either you go for the adversarial example where somebody is out to target you specifically, or just statistics. Anyway, you want to be sure that these things cannot happen.
Thank you.
Okay, so I'm trying to give you the motivation for the research problem that we want to solve. So we already saw a safety example with the Tesla that was hitting a road. These adversarial inputs are usually regarded as a security issue. And here's another example. This is a system called Aircast XU. So Aircast stands for Airborne Collision Avoidance System, and XU means it's for drones. So this is a system that is being developed by the American FAA, the Federal Aviation Administration, which is a main regulatory body when it comes to air traffic in the US. And the idea is that we have a lot of drones flying around and we don't want them bumping into each other. So the FAA wants to develop this system that is airborne. And so it's going to sit on an actual drone, that's us, in their terminology, the on chip is us. It's going to read some sensor information about an intruder. So the intruder is another drone that is nearby. It's not necessarily malicious, right? Despite the name, it's just another drone that's in the vicinity. And the system is going to read sensor information about speeds and distances and angles. So a bunch of physical information about the intruder with respect to the on-chip. And the system needs to make an advisory. It needs to tell the operator of the drone that the drone needs to make a strong turn to the left, a weak turn to the left, a strong right, a weak right, or it can give it a clear of conflict advisory, in which case it's safe to continue down the current trajectory. There's no risk of collision. So the motivation for these advisories is simply to prevent a collision between the on-chip and the intruder. So I think the statement of the problem is fairly simple, right? We know it's easy to understand what the system should do, but as it turns out, it's quite difficult to actually do it. So after a couple of attempts, the FAA actually converged at a solution that uses 45 deep neural networks. So this is a very interesting example. So you have a very respectable body, the FAA, and you have a very critical system, right? You don't want any collisions. And they want to implement them using deep neural networks. So this is another demonstration of how deep neural networks are really affecting many aspects of our lives. But of course, before they can do such a thing, they really want to be sure that these neural networks are correct. They want to be sure that there aren't any mistakes hiding in these neural networks that will only be discovered after deployment. So what are we trying to do in this context? So the idea is to take formal verification, which is a well-established field, and apply it to machine learning. So in formal verification, you want to formally prove that the program is correct. Right? So you have a piece of code that somebody wrote, and you have a specification, and you verify the specification on the program that you have. And either the formal verification tools tell you that your system is correct, or they say that your system is incorrect, and they give you back a counterexample. So this is formal verification. It's been around for many decades now, a well-established field. What does it mean to verify a neural network? Right, so this is a neural network. If you've never seen one, make your introductions. So the idea is that these neural networks have a big input space. And so this is the set of all possible inputs that you can give them. If you think about the Aircast XU system, for example, then the input space could be all possible configurations where the on-chip is in one place and the intruder is in another place, and you have all the possible speeds and angles. You take some point in the input space, you feed it to the neural network, and then it gets mapped to the output space, where the output space in the example of Aircast XU would be all the possible advisories. And what you do in formal verification of neural networks is you define a subset of the inputs P. This is the precondition. You define also a subset of the outputs Q, which is the post condition. And the question that you're trying to answer is, does there exist a point in P that gets mapped to a point in Q? And as it turns out, this very simple problem is what you need to solve in order to answer a lot of problems when it comes to neural networks. So typically, Q will represent the negation of the property that you really have in mind. So for example, P could mean that the intruder is very far away. So P will restrict me only to cases where the intruder is very far away from the on-chip. And Q will be the set of points where the neural network tells me to make a strong turn to the left. Right, so if the intruder is very far away, I expect that the network will tell me clear of conflict, that I can fly straight. So in this case, Q will be something bad. Right? I don't want any point in P, which should be mapped to clear of conflict, to get mapped to strong left. So you take this problem, you give it to a verification tool, and either the verification tool tells you SAT, that the problem is satisfiable, in which case it discovers a counterexample. It gives you back a concrete point in P that gets mapped to a point in Q, and you can actually test it and see that there is a problem. Or alternatively, it will say unsatisfiable, there is no solution to your problem, no point in P can get mapped to a point in Q, in which case you are happy. You know that this bad behavior does not happen. So this is the problem that we're trying to solve. I will stop again for any questions.
Just a question. So the input space though might not be that well defined. Right? I mean, suppose the input space is an image, right? It might not be so easy to say what you want the input space.
Right. So, okay, so this is a great question. So in verification in general, we know that it's very difficult to define P and Q. Right? That has nothing to do with neural networks. In traditional verification, we know that it's very difficult to get engineers and designers and modelers to tell you what P and Q should be. This is the same issue in neural networks. It's sometimes difficult to define what P and Q should be. I will talk a little bit more about it later, but for now, we're just defining this is just a problem statement, right? You for now assume that somebody gives you P and Q, and this is the problem that you want to solve. But this is a great point. I will come back to it.
Right. But in traditional verification, normally you have some handle on the P. Right. For the neural networks, perhaps the handle on the P is not so clear.
Okay, so traditional verification has existed a lot longer, right? So we know better what we want. Neural network verification is a little newer, so we're still trying to figure out what P and Q should be. Still, there are some things that people have been applying and trying. One thing that you can do is adversarial robustness. This is I will talk about. So this is one way to define P and Q. And there are several other domain specific properties and also universal properties that you can check. I prefer to get back to it a little later. Okay, so what does it mean to formally verify a neural network then, right? So you really want to formally prove a property or return a counterexample. And suppose for a second that you can do this, that you can solve the problem that I demonstrated in the previous slide. So there are many applications that you could use this for. So one of them is to check robustness for adversarial examples, right? So remember the panda and the slight perturbation that caused it to get misclassified as a gibbon. So one thing that you can do is you can formally prove that no matter how smart your adversary is, and no, they can never cause a misclassification in your network, right? So suppose you start with a panda and you say, my adversary is allowed to change 10 pixels, 20 pixels, or some other amount of distortion that you allow. You can formally prove that the network will never make a mistake. Okay, so this is a very strong statement because it doesn't depend on the specific adversary that is fighting you. Right? If you are able to prove this, then you know that you are covered. Even if tomorrow a very smart adversary comes along, they will not be able to fool your neural network. So this is one possible application, and this is one very famous and common example that many people have been using verification for. So this is one way to define P and Q. Another application is to formally verify that safety critical systems that incorporate neural networks don't make any mistakes. So for example, if you have the AKSXU system, the drone, and you want to make sure that there aren't any collisions, then really what you want to prove is that if you run the system that has a neural network in it, and you run the system for a while, then nothing bad happens. There aren't any collisions. So this is an even more complex problem. And to solve it, you can use a neural network verification core. And this is also something that many people have been looking into. And I think, if I'm not mistaken, you will hear a little bit about that today also. And finally, again, very much in line with the topics of today's masterclass, you can use verification to extract properties of networks and promote explainability and translucency of these models. So this is also a very active field of research. So these are just some of the things that you could do if only you could verify neural networks. So I hope the motivation is clear. Let's go back to the AKSXU example. So when we started working on this problem, we received from the FAA a list of properties that they wanted to show held for all possible inputs. So for example, the FAA want to show that if the intruder is distant, then the advisory is always clear of conflict. Okay, so this is your P, right? This is the input property, the intruder is distant, and this is your Q. The advisory is always clear of conflict. Well, Q will be the negation of this. So of course, this is given in plain English, which is not very helpful, but in this case, the FAA domain expert could translate this property into a well-defined logical formula. Right? So we know how to formally define this as a property mathematically. Another example, if the intruder is nearby and coming in from the left, then the advisory should be strong right. So if the other guy is coming at us from the left, then we want to escape to the right. So really, they have a bunch of these properties that usually make sense, and they can define them mathematically very accurately. And we want to prove them on the neural networks. And this was determined to be crucial for increasing the level of confidence. And so this is much better than just testing your neural network, because you are guaranteed that any possible input will satisfy these requirements. So this is really what we want to do. So I hope the motivation and the problem statements are clear. So now I want to briefly define what a neural network is. If you're not familiar, you will need this to understand the next stuff that I will show you. And then after that, I want to tell you a little bit about the ReluPlex approach for solving these verification queries. But for that, I will first need to tell you about Simplex, which is the basis for base for ReluPlex. And then finally, I will go back and tell you a little bit about the evaluation on ACAS-XU. So this is a deep neural network. So the idea is that this is just a graph, a weighted directed graph that is, the nodes are called neurons. They are organized in a layered structure. The inputs come in from one side. So if we think about the ACAS-XU system, this will be the sensor readings. And so the sensor readings, the values get inserted into these input neurons. And then you do this mathematical propagation where you each time compute the values of another layer and another layer and another layer based on the assignments of the previous layer, all the way to the output layer. And the output layer tells you what you should return to your user. Right? So for example, if you have 5 advisories, then you will have 5 output neurons, and the one that gets the best score is the one that you return to the user. So you say, my advisory is turn left if the turn left neuron got the highest score. So the thing about neural networks is that they are completely incomprehensible. Right? There is very little you can do if you take a large network that has hundreds or thousands or even millions of neurons. It's very difficult for a human to look and see and understand why the network makes any decision. So the ACAS-XU networks are not very large. They each have about 300 neurons, but that already was too much for a human to understand what was going on inside. So when we verify these neural networks, we want to show that an input property implies an output property. So for example, we want to show that if the intruder is distant, then this implies that the advisory is clear of conflict. So as it turns out, this problem is NP-complete in the size of the network. So this means that if your network has, for example, 300 neurons, as is the case in the ACAS-XU networks, then in the worst case scenario, you would need 2 to the power 300 actions. And so the usual issue with NP-complete problems. So this looks pretty bad, but in verification, we are not overly concerned about this because we know that practically in every case in verification, the problems that we are trying to solve are either very complex or even undecidable. And still there are many success stories. And the key point is that typically the worst case behavior does not happen in practice. And so we know that in the worst case, we will need an exponential number of steps, but in practice, we can often run a verification procedure much more quickly than that. So where is this difficulty coming from? Why is it difficult to verify neural networks? So if we zoom in at into just one neuron and see how it gets evaluated, we will see that the neuron is typically evaluated in 2 steps. First, you compute a weighted sum. Right? So you have neuron values in the previous layer that you have already computed, and each edge in your neural network has a weight. This is part of the neural network, and you just do a weighted sum. Okay? So in this case, the weighted sum that you get will be 4. And then once you have the weighted sum, you apply an activation function. So in this case, you have some function f. This is the activation function. You apply it on 4, and the output of f will be the value that you assign to this new neuron. So here is one famous activation function called a ReLU, rectified linear unit, which is defined as the max between 0 and the input. And so this is the graph of a ReLU function. If your input is negative, this is what we call the inactive phase. The function just returns 0. And if your input is positive, then this is the identity function. This is what we call the active phase. So if your weighted sum turns out to be positive, this is what we call the active case, and the next neuron gets evaluated 4. If the weighted sum turns out to be negative, as in this case, then we are in what we call the inactive case, and we instead get a 0 for the next neuron. So this is the ReLU. This is the rectified linear unit. It's a very common activation function, one of the more useful ones these days, and practically everybody is using it. So in this talk, we will focus mostly on ReLUs. Any questions so far? No. Okay. So what does it mean to verify a network that has ReLU activation functions in it? So typically what we have as part of our verification problem is a property. And so this is P and Q. And the property is typically a set of linear constraints on your inputs and your outputs. So for example, if you care about an intruder that is very far away, then you would say that your input constraint is that the input that signifies distance is at least 2,000 feet or whatever. right? And you might say that the network tells you clear of conflict, and you would say that the score for clear of conflict is greater or smaller than the other outputs. So all of these are linear constraints. And typically, all the properties that we are studying today, all the interesting properties that we know of, fall into this category, almost all of them. Then you have the neural network itself. So we said that the neural network is comprised of weighted sums and activation functions. So if you didn't have activation functions, if you only had the weighted sums, then the network would be completely linear. All the weighted sums would be, we will only have weighted sums, which are linear constraints. And then everything that we have would be one big linear constraint, and then we could solve it. And then we would be in what we call a linear program, LP. And we know in computer science that linear programming is very easy to solve. We have mature solvers like Gurobi and others that are very good at solving these kind of problems very, very quickly. So this would be very easy to solve. But then what you have is the ReLUs, right? So the only thing that is difficult that remains is these ReLUs, which are piecewise linear. Remember the graph that we saw last slide. And as it turns out, once you introduce these ReLUs, then the problem gets translated into an exponentially long sequence of linear problems. And so every problem that you need to solve will be simple, but you will have an exponentially long sequence of them, which is what is making the problem so difficult. So this is what we call the case splitting approach. And here's the basic algorithm. So first you make a guess, right? You look at all your ReLU activation functions, and for each of them you make a guess whether that ReLU is going to be active or inactive. Once you make a guess, if you guess that the ReLU is active, then you can translate it into an identity function, which is linear. If you guess that it is inactive, then you translate it into a zero function, which is again linear. So once you have made this guess for all of your ReLUs, you get a linear program that you can solve. You solve it. If you find a satisfying assignment, which is a violation of the safety property that you're checking, then you can stop. You know that you have found a concrete counterexample and your property doesn't hold, so you're happy. But if you are unable to find a satisfying assignment, then you don't know. Is it because really there is no satisfying assignment, or because the guess that we made for the ReLUs was not a good one? So in this case, we need to backtrack and try another option. So this is very, very similar to Boolean satisfiability. Right? You guess for each ReLU, you have two phases, true or false, active or inactive. You make a guess, you check, and if you guess correctly, you can stop. But if not, then you need to backtrack and try another option until you have exhausted all the possible options. So this is why you have an exponential blow. So let me show you what it looks like visually. So suppose you have a set of linear constraints like these ones, and then you have a ReLU constraint. So what you can do is you can guess, right? So first you can guess that the ReLU is active. So you take the linear constraint that you had and you add the translation of a ReLU to the active state, which means that the input is at least 0 and the output is the identity function. And then you solve this. If there is a solution, then you are happy. The solution will apply also to the original problem. But if not, then you need to check the other branch. You need to guess that the ReLU is inactive. So the output is 0 and the input is negative. So one ReLU leads to two guesses. 300 ReLUs will lead to 2 to the power 300 guesses that you need to check in the worst case. So this, of course, is not a proof, but this, I hope, gives you the intuition about why this is a difficult problem to solve. So in the ReLUplex project, or in more generally in the SAT and SMT-based approach to verification of neural networks, what we want to do is mitigate this state explosion. And there are some principles that we apply from the SMT literature to do this. So the most important one probably is the lazy approach. So the lazy approach says, instead of taking every ReLU and guessing whether it's active or inactive in advance, instead, very lazily try to solve the problem without doing a case split, and only do a case split if you determine that you have to, if you have no choice. And often we find that you don't really need to split on all the ReLUs when you do this. Another thing that we do in the SMT and SAT communities and can be applied to neural network verification is conflict analysis. So intuitively, this means that if you made a guess about your ReLUs and you were unable to satisfy your constraints, then you don't just naively proceed to the next possible configuration of ReLUs, but instead you try to understand why your current guess failed to give you any counterexamples, and you use this information to rule out other guesses that are guaranteed to not contain any counterexamples. So this is a very smart way for pruning the search space, which has been used in the SAT and SMT communities for a long time. And these principles already were sufficiently scalable to solve the AKSXU problem, which I will tell you more about towards the end of the slides. Any questions so far? Okay. So now I want to tell you about how to do this, about the ReLUplex algorithm. But to do that, I first need to tell you a little bit about Simplex. So here is our running example. Right? So it's a very small network, just 4 neurons. And for now, let's assume that there are no activation functions. So the 2 neurons in the center, the hidden neurons, we assume are just weighted sums. They're not computing any activation functions. So let's assume that this is the property that we want to check. Right? So our input property is that x1 is between 0 and 1. And the output property is that x4 is between 1/2 and 1. So our goal is to find a satisfying assignment to the neural network such that x1 is between 0 and 1 and x4 is between 1/2 and 1. Now, if you look at the network, you will see that no matter what you assign to x1, x2 and x3 will be x1 and minus x1. And because we have no activation functions, nothing will zero out. And then x4 will be x1 minus x1, so it will always be 0. So we expect an unsat result, right? Because x4 can never be between 1/2 and 1. So this is what we want to prove using Simplex. So Simplex is just an algorithm, a very famous algorithm for solving linear programs. So how do you take this neural network verification query and transform it into an input to Simplex? So first, every weighted sum that you have in the neural network gets translated into an equation. And so for example, if x2 equals x1, then you have this first equation. If x4 is x2 plus x3, then you have this third equation, etc. Every weighted sum gets translated into a single equality. And then you also have the bounds. Right? So x1 needs to be between 0 and 1, x4 needs to be between 1/2 and 1. And x2 and x3, you don't care about them. They're unbounded, they can take on any value, you don't care. So what you have here is a set of equalities and a set of variable bounds, which is precisely what a linear program is. And so this is how you can take the neural network verification problem and translate it into a linear program. There is an extra technical step. So Simplex, which we're going to use for solving this linear program, doesn't like these constants floating around. So we're going to replace the zeros with fresh variables, x5, 6, and 7. We're going to require that these 3 variables be precisely 0. So this is a purely syntactical thing. It doesn't change the satisfiability of the problem. It's not very significant. We just do it because Simplex expects the input to be in this form. So how does Simplex go about solving these kind of things? So Simplex is, again, just a method for solving linear programs, which are a set of linear equations and bounds. It's very, very efficient. It's sound and it's terminating. We will talk a little bit about that later. And as we said, it's very difficult to handle ReLUs with Simplex, but for that we will have ReLUplex later. So when you execute Simplex, what you do is maintain a variable assignment. So at each point you will have a current assignment to all of your variables. And you will make sure that the assignment always satisfies the equations that you have, but variable bounds may be violated, and you will gradually try to satisfy them as you go, incrementally. And in each iteration of Simplex, you have 2 steps that you can perform. You can perform pivot steps, in which you do simple manipulation of the equations, or you have update steps where you update variable assignments. And it turns out that just using these 2 steps, it is guaranteed that we will either converge the solution or prove that no solution exists. So I'm not going to define the algorithm formally. I just want to show you an example, and hopefully this will convey the main principles. So here is the problem that we wanted to solve. Right? So we have the equations from before. And this table shows us the current state of Simplex. So you have all of your variables. For each of them, you have an assignment. Currently, the initial assignment is zeros to all variables, which trivially satisfies all of the equations. And for every variable, we have a lower bound and an upper bound. Where a bound is missing, it means that the variable is unbound. So now Simplex tries to solve this problem. And in the first iteration, all the equations are satisfied, but we have a problem with x4. x4 should be between 1/2 and 1, but currently it's 0, it's too small. So in the first iteration, Simplex updates the assignment of x4, and it increases the assignment from 0 to 1/2. So it increases x4 until it meets its lower bound. So this changes the assignment for x4. And then we said that we always want to maintain the equations. So if we changed x4, we need to change also x7 because they are connected through the third equation. So the assignment for x7 also increases to 1/2. Now the first iteration is done, and indeed x4 is no longer problematic. It's in the side, it's within its bounds like we wanted. So that's good. But now we have a problem with x7. x7 is too great. It should be precisely 0, but it's currently 1/2. So what do we do in the second iteration? So x7, unlike x4, is a left-hand side variable. So when a variable appears on the left-hand side of an equation, we can't just change its value. We first need to turn it into a right-hand side variable. So this we will do by a pivot. A pivot means that we swap x7 and in this case x2, one of the right-hand side variables. Right, so we take this equation and we swap. So this is a very trivial arithmetic manipulation. And now x2 is the left-hand side variable and x7 is the right-hand side variable. So now x2 appears both on the left-hand side and on the right-hand side of another equation. So we're going to substitute x2 with this equation just to make sure that every variable is either left-hand side or right-hand side, but not both. So once we're finished with this, then x7 is now a right-hand side variable and we can just change its assignment. In this case, we can decrease it until it hits 0. So x7 gets decreased to 0. And in order to maintain the equations, x5 and x2 needs to be increased by 1/2. So both of them increased to 1/2. So this is how Simplex progresses, right? So in each iteration, it addresses one problem. In this case, it fixed x7. And this continues a little while longer. So I will skip the next iteration because it's really more of the same. Until at some point, you have a variable that is out of bounds. In this case, x6 is too great. And Simplex gives you back a failure notice. It says, I can't make any progress. And why is this? Well, x6, if you look, currently it's too great, right? It's 1/2 when it should be a 0. But the equation for x6 is x4 minus x5 minus x7. x4 is already pressed against its lower bound. So x4 cannot decrease. So it cannot help x6 decrease. And x5 and x7 both appear with a negative sign, but both of them are already pressed against their upper bounds. So they cannot increase in order to allow x6 to decrease. So in other words, the current assignment of x6 is a minimum. x6 cannot go below 1/2. And consequently, it is impossible to satisfy the constraint that x6 should be at most 0. So this is why Simplex tells us fail. Right? It tells us that it cannot find a satisfying assignment, which is exactly what we were expecting because we saw already that it was impossible to satisfy this property. So this, of course, is not a definition of Simplex and it's not a proof of anything. I just want to convey the basic principles of the algorithm. If anybody has any questions, please go ahead. You guys are all very quiet. Okay, so if we wanted to handle ReLUs with Simplex, then we would do precisely what we said before. We would do the case splitting. Right, so first we would guess, so now we assume that the ReLUs are back. So x2 and x3 have the ReLUs, the ReLU activation functions now. And if we wanted to apply Simplex to solve this problem, then we would first guess that both of them are inactive. Right, so we would translate, as we saw before, we would translate both of them to the inactive constraints and we would solve. And if we get answered, then we would try another combination. So we would guess that x2 is active and x3 is inactive. And then et cetera, all 4 combinations in the worst case, which, like we said, is exponential. Okay, so now comes the extension, right? So we want to take the basic Simplex approach and extend it so that it can handle ReLUs much better. So this is based on a joint work with the 4 co-authors listed here. It appeared in CAV 2017, and of course, it's also available online. So in ReLUplex, the first thing that you do in the encoding is to treat each ReLU constraint as a pair of variables, and instead of just a single variable. So each ReLU first gets split into one variable that represents the weighted sum going into the constraint, and another variable that represents the activation value coming out of the constraint. So the picture changes into this, right? So each variable is now split in 2. So we have x2w is the weighted sum that's going into the ReLU, and x2a is the activation result that's coming out, and likewise for x3. And we, of course, remember that these variables are connected through a ReLU constraint, but we also treat them as individual variables that can skew, right? So they don't need to immediately satisfy the ReLU constraint. They are each independent. And what we will do is, just like Simplex allowed variables to be out of bounds and then gradually fix them, we will allow our ReLU variables to temporarily violate ReLU constraints and then gradually fix them. So it's really a very similar principle, but applied also to ReLUs. So the encoding is very similar to what we had before, right? So for each variable that computes a weighted sum, we introduce an equality. So now we use the W variables and the A variables where we need to, according to the image that you see here. And the bounds, as before, we allow the input variable to be between 0 and 1, the output variable to be between 1/2 and 1. This is the property that we're checking. x5, 6, and 7 are the auxiliary variables, so we say that they are precisely 0. The w variables, the weighted sums, are unbounded. And the a variables, by the definition of a ReLU, they are non-negative, because a ReLU cannot output any negative numbers. So this is the translation of the problem into equations, bounds, and of course the ReLU constraints. So very similar to what we had with Simplex, but now with the ReLUs also. Okay. So here is now an example of how ReLUplex runs. So like before, we have the equations and we have the table with the variable assignment and the lower and upper bounds. And this time we also have the ReLU constraints, right? So we remember that x2w and x2a are connected, and x3w and x3a are also connected. And ReLUplex starts running just like Simplex. So initially, the only concern is x4, which is the only violated constraint. It's too small. It should be at least 1/2. So just like before, we do an update step. We increase x4, and consequently also x7, right? Because x7 depends on x4, so x7 also increases to 1/2. So in the first iteration, x4 is now correct, it's fixed. Next iteration, x7, too great. Again, we do a pivot step, followed by an update step. So x7 decreases, and x2a in this case increases. In the third iteration, if you look, all of the variables satisfy their bound constraints. But now we have a problem with a ReLU. And so now we have x2, which remember is a ReLU constraint. So x2w, the input is 0, and x2a, the output is 1/2. Which of course is a violation, but this goes against the definition of a ReLU constraint. So what do? Precisely what we did before. We do an update step in order to rectify this. So x2w is too small, so we say let's update x2w and increase its value to 1/2. And so the value of x2w increases, and then the value of x5, which depends on x2w, also increases. So this really, I think, is a key point, right? So this is very different from case splitting. In case splitting, we said we would first guess, right? We would say that x2w is that x2 is active or inactive, and this would give us the constraints that we needed. Here, what we do is we don't guess. We lazily try to satisfy the constraint. And so we on the fly attempt to make sure that it is satisfied, but without guessing in advance whether it's active or inactive. So this is a very opportunistic approach. So now x2, the ReLU constraint is satisfied, and we continue as before. So now x5 is too great. So we do the Simplex stuff. Again, more of the same, pivots and updates, pivots and updates. And this continues a little while longer until at some point we get a success notice. Right? So now all of our variables are between their bounds. All the ReLU constraints are satisfied. So x2 is satisfied in the active phase. The input and output are positive and equal to each other. And x3 is satisfied in the negative phase. So the input is negative, the output is 0. That's also fine. And the equations always hold, right? So all of our constraints are satisfied, and we didn't need to do any case splitting to do this. And indeed, if you grab the assignment from the previous slide and you put it inside the neural network, you will see that the assignment that we got indeed is a counterexample for the property that we were testing. So again, this is not a formal definition of the algorithm. If you want to see that, you would need to go to the paper, but I hope this conveys the intuition of how the algorithm works and how it attempts to circumvent the state explosion problem. Let me stop again for any questions.
So it mustn't always work out, right? So I guess you're going to tell us that next.
Yeah, so an excellent question. Next slide. Any other questions? Okay. So like Peter just said, so we know that the problem is NP-complete, right? So there's bound to be a problem somewhere. So we can prove, so what we care about is soundness and termination. So soundness is pretty straightforward to prove. So soundness here means that if ReLUplex tells you that the problem is unsat, then the problem is really unsat. And if it tells you that it has found a solution, then that solution will be correct. So that part is easy. The question is, can you always find a solution using just pivots and updates? Will the algorithm always terminate? So it turns out that no. Sometimes you can get into a loop. And intuitively, this will happen when you try to satisfy a ReLU constraint. So you update a variable one way, and then it breaks a bound, so you need to update it back into its original value. So you can have this loop that alternates between fixing broken ReLUs and broken bounds. So in order to guarantee termination, what you need to do is you may have eventually to split on some of the ReLUs. You may need to do case splits. So this will guarantee termination, but of course it will significantly increase the runtime, right? It will make your algorithm much slower. But like we said, we do this very lazily. So we don't split on the ReLUs in advance. We only split on ReLUs that we have determined are causing us problems, right? They're getting us stuck in loops. So only for those ReLUs we do case splitting. And in practice, for the AKSXU networks, for example, we had to split only on about 10% of the ReLUs. So this precisely sends you from 2 to the power of 300 to 2 to the power of 30, which is already manageable. Right? So this is a huge difference when you think about the exponential nature of the problem. So indeed, in the worst case, you will need to do a lot of splitting, but in practice, you don't need to do so much of it. A few other points that are important. So this, what I've shown you so far, is just what we call a search procedure. Right? So the algorithm goes through possible assignments and it tries to find a satisfying one. There's also deduction steps, which are very important, which allow you to rule out possible assignments and not have to search them. So typically in the formal, in the neural network verification literature so far, this is done by deriving tighter lower and upper bounds on variables. And I think you will hear more about that later today also. But just to give you an intuition, suppose you have this equation x equals y plus z that you have found as part of your simplex or ReLUplex execution. And you know already that x is at least -2 and y and z are both at least 1. If you have this information, then you can deduce a tighter bound on x. Right? You know by this equation and by these bounds that actually x can never be less than 2. Now suppose that x is part of a ReLU constraint, either as an input or an output to a ReLU. Then you immediately know that this ReLU has to be active, right? Because if the input or the output of a ReLU is positive, then the ReLU cannot be inactive. So every bound that you discover that teaches you something like this allows you to reduce the number of ReLUs that you have, which in turn expedites your solving process. So there's a lot of work, both in the original ReLUplex and in Marabou and in many other tools, on how to derive tighter bounds effectively. So this is a very active and interesting field of research. And there are some additional principles from the SMT framework that you will want to incorporate if you try to implement this approach, particularly how to do case splits and bound tightening efficiently using conflict analysis and CDCL tools, which I won't have time to go into today. And finally, there's an important aspect when it comes to floating point arithmetic. So there's a lot of issues here because neural networks are not computed usually using precise arithmetics. SMT solvers typically do involve precise arithmetic. So you run the risk of getting an unsound result, right? Because if your precise arithmetic solver tells you unsat, it doesn't guarantee that your actual implementation cannot have a counterexample and vice versa. So this is something that you need to think about. And if you use floating point arithmetic for the verification procedure, then you need to think also about inaccuracies and round-off errors. So this is all stuff that you need to keep in mind when you are talking about these kind of tools. So as Alexey mentioned earlier, we have already extended. So ReLUplex is from 2017. The next generation is a tool called Marabou. It has a lot of features that I won't talk about today, much better engineering, parallelism, a bunch of engines for doing network level reasoning, which is the sort of high level reasoning about a neural network that is not constraint specific, but rather a little bit more general. And really you can, if you're interested, you can download the tool and of course read more online. Okay, so we don't have much time left. So let me go back to the AKSXU example and tell you a little bit about the evaluation. So like we said, the FAA gave us a list of properties that they cared about. So what they did before was simulations. And so this is what they call an encounter plot. So they take, this is the own chip here in the center, and this is the intruder. They fix many of the parameters of the problem, and with the remaining parameters, they do simulations on many possible values, and they draw this plot. So this plot shows you the advisory that you get based on the location of the intruder. So if the intruder is very far away, or if it has already passed us, then it is in the white region, which is clear of conflict. If it's coming at us from the left, then the advisory is weak right. If it's closer, then it's already strong right. Likewise, strong left and weak left. So intuitively, if you look at this in these encounter plots, you see that the network sort of behaves like you expect, but of course, you're not guaranteed that there aren't any bugs hiding in points that you didn't sample. So the FAA defined a list of 10 properties that they wanted to check. So no unnecessary turning advisories, that alerting regions are consistent, and that strong alerts not appear when the vertical separation is large. So these are all things that they really care about, and they defined a set of these things and wanted us to verify them on the neural networks. So first example, if the intruder is near and approaching from the left, then the network advises strong right. So this was formulated as a set of linear constraints on the inputs and the outputs of the network. And here we were able to prove the property successfully, meaning that we were able to show that for any input among these infinitely many inputs that satisfy these constraints, the network always behaves correctly. Another example, if the vertical separation is large, meaning that the two aircraft are very far away vertically, and the previous advisory is weak left, and the network now advises clear of conflict or weak left. Again, this was formulated mathematically, rigorously. And here we were actually able to discover a counterexample. So we were able to come back with a concrete input on which the neural network fails to operate correctly. And then you can use this information to retrain your neural network or to add manual override rules in order to make sure that this bug does not happen after deployment. So this is an example of applying formal verification to verify a safety critical system. Now let's also talk a little bit about adversarial robustness. So the measure of robustness is sort of the opposite of adversarial examples, right? So if your network is susceptible to adversarial examples, then this means that a small perturbation is enough to fool it, to make it misclassify an input. So adversarial robustness is a measure of how difficult it is to do this. So we say that if a network is robust, then you will need a lot of perturbation, a lot of noise in order to fool it. So it turns out that you can cast this as a verification query. So what we did here was we took 5 input points for the AKSXU networks. So each row in the table is an input point. And each column represents the amount of noise, the amount of perturbation that the adversary is allowed to use. And the verification query that we asked was, given these conditions, so for this point and for this amount of noise, can you find an adversarial example? So you see that for some points, for example, points 2 and 3 and 5, the network is fairly robust, right? Even if you allow a large amount of noise, assume that this is a large amount, then the network is robust. Even the best adversary in the world will not be able to fool it. However, if you look at points 1 and 4, you will see that for small perturbation, they're okay. But once the perturbation slightly increases, then already you can find a counterexample. Right, so this lets you really understand how robust your neural network is before you deploy it, even against attacks that you are not yet familiar with. So this corresponds a bit to the question before about how to define P and Q. So this is one property that is what we call universal. Right, the AKSXU properties were domain specific. The FAA engineers had to tell us what to check. This property is a little bit more universal. Right? It doesn't matter what your neural network does, you really expect it to be robust. Let me stop again for questions.
Okay, we've got a question from the live audience. Earlier you mentioned that in your implementation you integrated this with SMT. I just want to ask, how exactly did you integrate this simplex method? So it's like in a custom theory, or more like in a propagator, like you have, if this is active, then you check this simplex condition, or?
So there are several ways that you can do this, but the most common one, I think, and the one that we used, was to think about the component that solves linear arithmetic plus ReLUs as a theory solver inside your SMT engine. And then the SMT core can do the case splitting for you. And this is just a regular split that an SMT solver does. And then the SMT engine will manage for you CDCL and all that stuff, the backtracking and all the stuff that an SMT solver does.
Yes, thank you.
Another question. So the simplex solver, did you guys have your own solver, or do you use one of the state-of-the-art simplex?
So in ReLUplex, we used GLPK, which is an open source LP solver that you can download for free. Since then, in Marabou, we have our own internal simplex solver that we use, and we also use Gurobi for dispatching some queries. So it's really a combination. So Gurobi is, I think, now used in most neural network verification engines. It's a very, very powerful tool. And of course, the problem with a black box tool is that you cannot look at the insides and modify it easily. So we use Gurobi for queries that are black box. We just need an answer. But for the search procedure that I showed you, where you need to interfere with the internals of the simplex solver, then we have our own engine that does that.
There's also a question in the chat from Peter Stuckey.
I guess I can talk. I was thinking about maybe it should be left for the end. It was very technical. So you talk about the Reluplex basically can get into this looping behavior. Do you actually track the loop and sort of try to work out a causal chain of events and use that somehow?
Right. So in Reluplex, the original algorithm that we used said just count. Right. So for every rel, you count how many times the rel gets broken and you need to fix it. And once the rel hits a certain threshold, do a k-split on that rel. So this is a fairly simple way for doing this. Nowadays, there are better techniques. We call them sum of infeasibilities, and there are also some other names for them. But the idea is that you collect a lot of information as Simplex runs, and you try to identify which values are the most problematic ones and split on those. So there's a lot of information that you can extract from the Reluplex iterations and try to decide which values are key for splitting.
Right, but you're not actually looking for chains of behavior that sort of from this ReLU change, changing the state of this ReLU led back to itself somehow. So
the counting procedure with the thresholds sort of does it, but at a very naive way. You could, I'm not aware of a more clever approach today, but it's an interesting direction.
Okay.
Okay, so let's, we're almost wrapping up. Okay, so this little variant that I showed you here is called local robustness. So we pick 5 points, and for these points, we evaluate the robustness. But you could say, okay, that's very nice, but this is only for 5 points. What about the rest of the input space? Or you could say something else. You could say, okay, for a point x1 that is deep in the weak right region, for example, I expect a high level of robustness. But what about a point x2 that is on the natural boundary between two labels? For x2, even a robustness of 0 is probably okay, because if you do slight perturbation in one way, you're in the white region, and if you do a slight perturbation in the other way, then you're in the weak right region. So, it's not immediately clear how to take local robustness and make it useful. So for that, we have global robustness, which is defined slightly differently. So global robustness says that if you have 2 points, x1 and x2, that are nearby, so the distance in the input space between x1 and x2 is not large, then you want the confidence level that the network assigns to each label to be similar in x1 and x2. So intuitively, this means that there are no spikes. And if you start at a point and you move just a little bit, then your output will not spike significantly. So this is what we call global robustness, and you can check this for a whole set, even the entire input space simultaneously. And it also satisfies, it can handle the cases where you have points on the boundaries between labels. The downside with global robustness is that it's much more difficult to check than local robustness. So I think this is what we want to be doing, but so far we are sometimes looking only at local robustness because it's easier. So this is an active direction of research. Okay, so let me conclude. So neural networks are really everywhere today. They're acting as controllers for safety critical systems. There's an urgent need, and this is something that we are really feeling from industry, and of course in academia people are interested, but also in industry, that there is an urgent need for techniques to reason about neural networks. The SMT approach that we talked about today incorporates principles from the SMT solving, namely laziness, deductions, and conflict analysis. And as far as the next steps, so this is a very, very active field. Some of the directions that I think are very promising are first, abstraction refinement. So we know that verifying neural networks is difficult because the networks are large. So there are now ideas on how to take a neural network and make it smaller for the purpose of verification, to turn it into an abstract network that is smaller and verify it, which I think has a lot of potential. Looking for additional applications is also very interesting. So people today are focusing primarily on local robustness because it's very easy to define. We are looking for more interesting application domains, particularly in industry. For example, you can talk about network simplification, where you take a network and you make it smaller using verification, or you have networks that have watermarks and you can check the resilience, etc. There are many interesting applications, and we are actively looking for more. And of course, one of the key challenges is scalability. So improving the search procedures, improving the deduction procedures, these are all very, very active fields of research. Okay, so thank you for listening. I'll be happy to answer any additional questions. And that's it.
Thank you very much, Guy. That was a very interesting talk. There are a couple of questions in the chat.
Right.
The first one, is the perception of humans always robust?
So I think not, right? You have all these cool images on Facebook that will make your site blurry and show you that your vision is not as robust as you think. But in the original definition of robustness, the goal was to make sure that neural networks do not make a mistake where humans do not make a mistake. Because then there was the fear that somebody would come and make a small change that you will not see with your eyes, but the neural network will see and will respond incorrectly. So it's difficult to define precisely what robustness should be in the sense of neural networks. This is also something that we are looking into.
I see that Ronald wants to ask a question.
So that you mentioned that the problem was NP, but that's really because you use a ReLU, right? So ReLU forces it to be either one side or another side, right? But if you use something like soft plus or something like this, then the thing becomes continuous and differentiable, blah 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 blah. Then I assume that it's no longer in NP. Right? I'm not sure what the complexity is, but it's probably no longer in NP.
Right. So you're correct. So the NP completeness comes from the piecewise linear nature of ReLUs. This will be the same for all other piecewise linear functions like leaky ReLUs, max pooling, all that stuff.
Is an artifact a choice or whatever?
So people have also been looking at non-piecewise linear functions like hyperbolic tangents and sigmoids. I'm actually not sure what the complexity is for that class of problems. Intuitively, it's actually more difficult. People have not had much success working with those. One technique that people are doing is actually to approximate those functions with piecewise linear functions. So you basically take a sigmoid and you upper bound it and lower bound it using a piecewise linear function, and then you solve using existing techniques. And there are some abstract interpretation techniques that tackle sigmoids directly. So far, I think it's actually considered more difficult than ReLUs.
So you mean the going the NP route is better than going the continuous route?
So so the majority of neural networks out there today use piecewise linear functions. So you definitely want to solve those. Some networks still use non-piecewise linear stuff, primarily recurrent networks, for example. They have inside their LSTMs and GRU gates, they have non-piecewise linear stuff. So you want to support those as well. I'm not sure if there is a theoretical hardness result, but in practice, it seems to be more difficult.
Okay.
There's another question in the chat. As this approach seems to exploit linearity everywhere, how well does it cover the real-world neural networks? Are those really pure in regards to consisting of splittable linear activations only? The activation example looked like a policy network opposed to the value network, where I maybe expected a non-linear softmax activation in the final layer to normalize the output PDF. Isn't this not too common anymore?
Right. So softmax layers are typically used for training, but when you deploy a neural network, the softmax layer doesn't matter, because typically if you have a classification network, then you only care about which score is the highest. So the score that was highest before the softmax layer will still be the highest after the softmax layer. So we can just ignore the softmax layer and verify the network without. So the softmax layer is not an issue. Then you ask, okay, so in the neural networks internally, in the hidden layers, do I only use ReLUs and maxes and leaky ReLUs? And the answer is that in many cases you do. Another answer that is, if you know how to verify these, then you can convince people to use these neural networks. If you promise, if you go to an industry partner and you say, if you just make your network only use ReLUs and maxes, I will verify it for you, then maybe they will do. And the third angle is indeed to support non-piecewise linear stuff, like we just said. And this corresponds, this will be important, for example, if you want to verify recurrent neural networks. So this is also something that people are looking into.
Thank you, Guy. So I guess we should thank the speaker again, and we need to proceed. Thank you very much for the talk.
Okay, thank you for the invitation and for listening.